Hi there. So this video is going to give you a preview of complex numbers, which will be your imaginary numbers in your Math 171 class. At the top of the set of notes, you'll see here that I have revisited simplifying square roots because, as you'll notice as we move down, we'll also be looking at taking the square roots of negative values. So we'll need to be sure that we remember how to reduce square roots. If you need a lot of extra practice with reducing radicals, then I will refer you back to the very first folder in Math 171, Math 071 coursework. The very first weekly coursework folder had a video and had a preview on reducing radicals where I talk extensively about how to do this. Quick little recap here, though, would be that whenever you are reducing radicals, you want to keep in mind your perfect squares. And so remember, your perfect squares are 4, 9, 16, 25, 36, 49, and so on. Then remember, you generate this list from 2 squared, 3 squared, 4 squared, 5 squared, and so on. So here in example 1, when they're perfect squares, we can just easily take the square root. So the square root of 4 is just 2. Remember, square root just means what can you multiply times itself to get that number underneath the radical. Not all square roots are nice and perfect, so if I scoot on down here to letter E, the square root of 12, that's not a perfect square root. I can't take a number and multiply it times itself and get 12. But I can reduce this, so I look for the highest number in my list here that will divide evenly into 12. And hopefully you agree that would be a 4. 4 times what gives you 12? That would be 3. Now take the square root of what you can. We know the square root of 4 is 2, so that comes outside the radical. 3 stays inside, and that would be your final answer, 2 square root of 3. Okay. I encourage you now, stop the video, finish up example 1 here, make sure that you're tracking with simplifying square roots. Now, as we move on, we'll introduce the idea of an imaginary number. Imaginary number is denoted as a lowercase I here, and it's the square root of -1. So imaginary I is the square root of -1. I squared then would be equal to the square root of -1 times the square root of -1, and anytime you take a square root and multiply it times itself, you always get what's underneath. So essentially then we can say that I squared equals -1. So I is equal to the square root of -1. I squared is just -1. We'll talk about I cubed and I to the 4th in your 171 class, but we'll just focus here on I and I squared. In example 2, they want us to simplify these expressions. So I'll do a couple of these here with you. Okay, so in example 2, let's do letter A and letter B. These are perfect squares. Think about this, we know that if it were just the square root of 16, we'd just say, oh, okay, well that's 4. Well, let's think about a way that we could rewrite 16. We could rewrite 16 as -1 times 16. Agree with that? I mean, that means the same as -16. Now, look at what we just defined. We just defined that the square root of -1 was I, and we know the square root of 16 is 4, so therefore our answer here would just be 4i. That would be your final answer. You don't have to write all those steps, but I just wanted to break it down for you just so that you could see, where the I came from. That -16 could break down into -1 times 16. We know that the square root of -1 is I, so there's your I, and the square root of 16 is 4, like that. So then when you got to letter B, you could say, okay, well, since it's the square root of 81, I know the square root of 81 is 9, and because I've got the negative in there, it's going to be 9i, and that would be your final answer. Okay? Once you try C and D, let's come on down and let's look at E and F. In letter E and F, these are not perfect square roots, so we think about our list again that I wrote for you at the top of the set of notes here. Highest number in that list that will divide evenly into 72. Hopefully you agree with that would be 36. So -72, would you agree, could be the same as -36 times 2? That still gives me -72. Now, take the square root of what we can. We know the square root of 36 is 6. Because it's negative, it's going to be 6i, and then we leave the square root of 2 underneath the radical. I'm okay if you leave it like that, but I'm pretty sure that MyLab Math is going to want you to write it like this, 6 square root of 2, and then put the I on the outside. That I is not underneath the square root, okay? So just so you're aware of that. 6 square root of 2 times I. I mean, and this is really fine as well, but they're just a little pickier, so we just want to make sure that we're directing you correctly. All right, let's look at letter F. I've got this negative sitting out here already, so I'll keep it. How can I rewrite negative 60? Thinking about the highest number in our list that will divide evenly into 60. We agree with that would actually be 4 times 15. So I'm going to say negative 4 times 15. I always attach the negative to the value that I'm going to take the square root of because we know that the I is going to come out. So the square root, so I'm going to bring down my negative. The square root of 4 we know is 2. Because it's negative, it will be 2i. And then the 15 will stay inside. And then we'll just rewrite it. It says negative 2 square root of 15. And again, that I is outside, like so. That's your final answer. Okay, I'll let you try G and H. Move on down, your next fact. The standard form of a complex number is always A plus BI. A is the real part, B is the imaginary part. Okay, so some examples of numbers that are in standard form. For example, down here, 2 plus 3i. 2 is the real part, 3 is the imaginary. Negative 4 plus 6i. 3 minus 9i. Okay, the number in front is the real part. The number in front of I is the imaginary part. I'm going to do all of example. I'm actually going to finish up the rest of these notes. I'll do each example here with you so that you'll, when you see that in class, that you'll have been exposed to it. So down here in example 3, we're just doing an addition, subtraction, multiplication with imaginary numbers. So in letter A, we are just adding these two parentheses here together. So essentially that just boils down to us combining like terms. We're going to combine the real parts. 2 plus 5, of course, is 7. Combine the imaginary parts. 4 minus 3i would be a minus. You can, oh, I'm sorry, be a plus. Actually be a plus, wouldn't it? 4i minus 3i, that'd be a positive. You can put a 1 in front of your I, or you can just say 7 plus I. Either way. Okay. Letter B, just like we've talked about before. Just a second. That moved on me. Letter B, just like we've talked about before. You've got a negative sitting in front of that back parenthesis, so that negative 1 needs to be distributed. So let's burn a step here. I have 8 plus I. Take this negative 1 and distribute. So minus 1 minus 6i. Now, do like we just did. Combine like terms. So 8 minus 1 will give me positive 7. Combine my imaginary pieces. 1i minus 6i. So minus 5i. So 7 minus 5i. Final answer. Now hopefully you recognize in letter C and letter D, in order to find these products, we're going to use the FOIL method, or you can do multiplication as well, but FOIL method is how I've always been doing it, so I'll continue to do it that way. I'm going to multiply the first terms of my parentheses, so 3 times 7, 21. Outside terms of my parentheses, 3 times negative 1i, so minus 3i. Inside, 2i times 7, so plus 14i. And then last, 2i times negative I, minus 2i squared. Couple steps here. Okay, so now my next step is that I'm going to combine like terms. So I have 21. Negative 3i plus 14i is going to give me positive 11i minus 2. Now, in place of I squared, we know what I squared is. I'll come back up here and draw your attention to that. I squared is equal to negative 1. So we can, down here, replace I squared with negative 1. And now let's burn an extra step. So I have 21 plus 11i. Negative 2 times negative 1 will give me positive 2. And now lastly, I've got like terms, 21 plus 2, 23 plus 11i. Final answer. Okay. And then let's look at letter D. Essentially the same thing here. I'm foiling. I've got first 4 times 4, 16. Outside, 4 times negative I, so minus 4i. Inside, I times 4, so positive 4i. And then last, I times negative I, minus I squared. This time, what happens to those middle terms? Hopefully you agree. One's positive, one's negative, so they cancel out. That leaves me with 16 minus, now remember, in place of I squared, we know that that's negative 1, so 16 minus a negative 1 will land me at positive 17. That last example was actually a special case. If you'll notice, that this is 4 plus I and 4 minus I. Those are referred to as conjugates. Anytime you have A plus BI and A minus BI, those are referred to as conjugates. Essentially, the only thing that was different between these two terms here was that one was positive, one's negative. So that's the only difference here. In order to be a conjugate, one's positive, one's negative, but everything else stays the same. And when you multiply the conjugates together, you always arrive at a whole number. So in example 4, it says they want us to write the complex conjugate of the complex number and then multiply it. So if I'm giving you 9 plus I, then its conjugate, remember the only thing you change is the middle sign, so it would be 9 minus I. Now they want us to multiply this. So just like we just did, we FOIL this. 9 times 9, 81. Outside, minus 9I. Inside, positive 9I. Last, I times negative I, so it'll be negative I squared. Sure enough, what happens to those 9 i's? Cancel out. I'm left with 81 minus I squared is equal to negative 1. Two negatives side by side become positive. 81 plus 1, 82. So that's the fact just below here. Anytime you multiply a complex number by its conjugate, you will always get a whole number. And that's actually a technique that we'll utilize in this section in your 171 class, because it's actually not legal for us to leave imaginary numbers in the denominator. So you'll see that technique of using the conjugate in the 171 class. All right, and then lastly here in example 5, you're just multiplying. So you might want to try, probably be a good idea here to pause the video and try this one and get it as far as you can, and then come back to the video for the explanation if it doesn't match what you see on the solution key. So if I am multiplying here, I just multiply straight across. So up top I'm foiling, and on the bottom I'll also be foiling. So up top, when I FOIL, 4 times 4 will give me 16. Outside plus 4I, inside all another 4I, and last I squared. On the bottom, when I FOIL down here, 4 times 4 of course is 16, plus 4I minus 4I minus I squared. Now sometimes folks want to start saying, well, can I just cancel out these 16s and these I squares? That is not legal. The only way you could do that is if it was 16 up top, if it was 16 times all this, and on the bottom also 16 times all of that. That's the only way that you can cancel things out. But anytime you have addition and subtraction signs, you got to be able to cancel out the whole piece. And unfortunately here, if you'll notice up top, as we start to reduce, the 4 i's up there do not cancel out. So let's start cleaning this up a little bit. So up top I have 16 plus 8I plus, now that I squared turns into negative 1. On the bottom I have 16, now this time positive 4I, negative 4I, they cancel out, minus, and then we know that I squared is negative 1 down there. You tracking with me? Now on the bottom, those two negatives side by side turn into a positive, and so 16 plus 1, 17. That's the idea. I wanted to get rid of those i's in the denominator, okay? And then up top, 16 minus 1, of course, is 15 plus 8i. And then that would be your final answer. I do believe that they will, in my lab math, it will break it up into the real part plus the imaginary part, like that. So 15 over 17 plus 8 over 17i. Okay, just so that you're aware of that moving forward. Okay, let me know if you need anything. Thanks a lot. Bye.